Okay, so as we continue our exploration of the motion of rigid objects in 3D, I think we're going to go ahead now and take a look again at the motion of a top, and again I'm drawing a top that looks suspiciously similar to a compass, but hey. This time though, we're going to allow there to be a torque on the top. So let's go ahead and make this my z-axis here. We can call that one y for all it matters. This will be my z prime axis and my y prime axis. So, and we're tilted over some angle theta. So now I've flipped the prime, no prime notation back to what your book does. So it's the reverse of what I've done in the previous video. Okay, so anyway, the center of mass of the top is located here. And so we have a force of gravity acting on it there. And also we have a normal force acting up on it right there. Okay, now I chose my axis through the point of contact with the floor, so we don't have to worry about the torque due to the normal force. So, I mean the torque about our x prime axis, which is going out of the page, will be equal to mgl sine theta, where L is the distance from the point of contact to the center of mass. And the torque about the y prime and z prime axes are both 0. All right. So following this thought here, the x prime component of the angular momentum will be equal to the ix omega x, those are all primed, so it'll just be equal to I theta dot. And similarly, since it is symmetric, y prime, y prime, omega y prime, that's going to be equal to, again, I, because the off-axis components will be the same, the non-z-axis components will be the same. And following our prescription from our Eulerian angles, this will be phi dot sine theta. And then finally, the z prime component, I z prime, omega z prime. Okay, well this is different. Your book calls this I sub s for the moment of inertia about the spin axis. Good name as any. And our results from the Eulerian angles give me phi dot cos theta plus psi dot. And we're going to call that quantity in parentheses there the spin. Okay. So going back to Newton's law applied to rotations, in a fixed coordinate frame, the torque would be equal to dl dt. So that means in the body or the rotating frame, the torque would have to be equal to dl dt plus omega prime cross L. Oops, not prime, just cross L. All right, and we'll call that double star because we'll be getting back into it. All right. So we remember that in our primed system, omega x prime is theta dot, y prime is phi dot sine theta, and z prime is phi dot cos theta. Just keeping that in the back of our mind. Alrighty then. So we can write our dl dt. That's going to be equal to, as I differentiate this through in the primed frame, I've got an I theta, right? So this becomes I theta dot. That'll become an I theta double dot about my x prime axis plus I, so now picking out the other pieces here, we'll get a phi double dot, differentiating that, sine theta plus, differentiating this part of it, phi dot theta dot cos theta EY prime hat. And then plus our IS, and we'll just go ahead and call it S dot. Leave it alone for the moment. All right. Also, our omega prime cross L, that will be determinant here, EX prime, EY prime, EZ prime, theta dot, phi dot, sine theta, phi dot, cos theta, I theta dot, I phi dot, sine theta, and IS. So we go ahead and evaluate it. We're going to get an EX prime. That will be times IS S phi dot, sine theta minus I phi dot squared sine, theta cos theta plus EY prime I theta dot phi dot cos theta minus IS theta dot S. And then the last term just works out to be 0. So that's what we got left. All right, so now we can equate the components. Of our double star. So Newton's second law for rotations in the rotating frame. So when we do, we get that the x prime component of the torque, which we know is mgl sine theta, we get that that's I theta double dot plus IS S phi dot sine theta minus I phi dot squared cos theta sine theta. The y prime component of the torque we know is 0. And we can write that, just to save space, I'll say ddt of phi dot sine theta minus IS S theta dot plus I theta dot phi dot cos theta. And then finally, nz prime equals 0 equals IS times S dot. All right, let's go for the low-hanging fruit. This immediately implies that the z prime component of the angular momentum, which is equal to IS S, remains a constant. All right. The next step is going to be to look at the y equation of the torque. So I've got so I've got that 0 is equal to I times d dt of phi dot sine theta minus is s theta dot plus I theta dot phi dot cos theta. All right. I can certainly go ahead and multiply both sides. I can multiply this across by sine theta. The reason I do that, so this becomes I d dt of phi dot sine theta times sine theta minus is s theta dot sine theta plus I theta dot phi dot sine theta cos theta. The reason I do that is because I can rewrite it as d dt of I phi dot sine squared theta plus is s cos theta. And we look at all that and we recognize that that is the z component, not the z prime, the z component of the angular momentum. All right. So let's go ahead and get our LZ from our LZ prime. So L, so this is now in the fixed frame, will equal L inverse dotted with L prime from the body frame. All right. So there's following the kind of the example we did before. Again, here there will be no need to invoke a psi. So this is lambda theta dot lambda phi dotted with L prime. So taking the inverse of that, that'll be L phi inverse dotted into L theta inverse, because remember you gotta flip the order, dotted into L prime. All right, so that will be cos phi minus sine phi, because it's the inverse. Sine phi, cos phi 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, cos theta minus sine theta, cos theta. So we moved the minus signs in order to do the inverse, which is also thankfully the transpose, so it's easy to do. Lx prime, Ly prime, Lz prime. All right. Go ahead and do the matrix multiplies, and you get that Lz is equal to Ly prime sine theta plus Lz prime cos theta. All right, and substituting in for what those are, that's I phi dot sine squared theta plus is s cos theta. Cool. So the moral of this is that both Lz prime and Lz are both constants. Now the question I have for you to think about for a moment is, why is this not surprising? Think about, pause, and I'll get back with you. Okay, it's not surprising because the torque vector is directed along the line of nodes, and that's perpendicular to both z prime and z. Okay, so now that we've milked the ny prime, we're left with the nx prime equals, which you know is equal to mgl. Yeah, I can mgl sine theta, and we note that that is ISS phi dot sine theta minus I phi dot squared cos theta sine theta. All right. Now, in the very not too distant future, we'll attack the more general cases shortly with some other methods, but we can look at the case of steady procession immediately. So here's my z-axis, there's my origin, and my top is fully sticking out sideways. So there's my z prime, then the old z-axis, the lab frame z-axis, is the y prime axis, and obviously that's a right angle. Okay, so here theta equals 90 degrees, but more importantly it's equal to a constant. So since it's equal to a constant, that means that theta dot and theta double dot are both equal to 0, and that is what we call the steady procession condition. So with that, we can go ahead and put in the 90s for theta here and get sine of 90 is 1, but cosine 90 is 0, so this right-hand term drops. Sine of 90 is 1, so the nx prime equation becomes mgl equals ISS phi dot, and you treated that in your lower division mechanics class. All right. Now what if, whoa, theta is unequal, man, theta is unequal to 90 degrees. Well, in that case, our nx prime equation becomes, well, the torque will be mgl sine theta. That'll be equal to ISS phi dot sine theta minus I phi dot squared cos theta sine theta. So at least the small favor is all the sine thetas cancel. All right. Now we can solve this for phi dot. So we'll get into standard form first. We'll have a phi dot squared times I cos theta minus phi dot ISS plus mgl equals 0. That's a quadratic in phi dot, so we can solve for that with the Pythagorean theorem. So we get phi dot is equal to ISS plus or minus the square root of ISS squared minus 4 mgl I cos theta all over, let's see, 2a is going to be 2 I cos theta. Now, there are two branches to this, so we call this fast procession. and the lower branch gets called slow procession. And which root is the one you want depends on the initial conditions, although it usually turns out that it's going to be slow procession. All right, now to have a physical solution, we can't have phi dot go complex. And so that means that the quantity in the radical has to be real. So that requires that is squared s squared be greater than or equal to 4mgli cos theta. So that's our stability condition. If we don't meet that, then we're not going to have procession. In fact, what's going to happen is it's just going to flop over. So we can go look at a sleeping top. That's one for which theta is equal to 0 degrees. So in that case, we put in 0 for the cosine, we just get 1, right? So you get that phi dot is equal to ISS plus or minus root is squared s squared minus 4 mgli all over just, now it's just 2I. So my stability condition is that the spin, on the spin, is squared s squared, I have to be spinning fast enough that this quantity is greater than 4mgli, or else I just plain flop over. Okay. So with that, if you actually spin a top, though, you'll find steady precession doesn't happen a lot. If you get something processing around, you can just kind of give it a little nudge, and you'll see the rotation axis bob up and down while the procession is occurring. That bobbing up and down gets called nutation. So nutation, U-T-A-T-I-O-N. So that, yeah, let's try writing it again. N-U-T-A-T-I-O-N. All right, so let's assume that, you know, I'm in some sort of little stand or whatever, and this is nice and frictionless here. So then there's one end of my gyro, there's the other end, and there's the rest of it. Okay, so again, normal force, gravity, like so. This nutation, it's going to bob up and down. So we'll say that the angle we make with respect to vertical is theta, and that as we bob back and forth, we will bob back and forth between angle theta 1 and angle theta 2. Sorry for the clutter there. That's the end game that we're getting to. So now let's go ahead and derive that. Now if we look at the energy equation, the energy is going to be 1/2 I omega squared, so we can write that. That'll be I omega x prime squared plus I omega y prime squared plus is omega z prime squared plus the potential energy, mgl. We can do better than that. There we go. Plus mgl cos theta, and that has to equal a constant. All right, so putting in what those are, our constant has to be equal to 1/2 I theta dot squared plus I phi dot squared sine squared theta plus IS S squared plus MGL cos theta, and we'll call that triple star. All right. Now, if we go back to our ny prime equals 0 condition, we can deduce, we can get from it that that requires that I phi dot sine squared theta plus IS S cos theta equals, we'll call that LZ, equals a constant. We saw that already. All right, so drilling down on my phi dot, which is the name of the game here, I phi dot sine squared theta would be equal to LZ minus IS S cos theta, but that ISS is LZ prime. So we get that that's equal to LZ minus LZ prime cos theta. So finally, we get that phi dot will be equal to LZ minus LZ prime cos theta over I sine squared theta. Okay, now that looks like a mess, but look at that for just a moment. When you look at this, the phi dot, there's nothing that depends on time or anything like that. This depends solely on theta. So when we put that back into our energy relation here, we're going to get an expression for this guy that depends solely on theta. And that's going to allow us to clean this up quite a bit. So plugging into triple star, that's now going to yield us that the energy is 1/2 IS S squared plus 1/2 I theta dot squared plus 1/2 I, and now we'll substitute in my phi dot squared. It'll be LZ minus LZ prime cos theta over squared over I squared sine squared theta times sine squared theta plus MGL cos theta. All right, cancel, cancel. We can partially cancel one of those i's. All right, now let's go and look at this. First off here, this bit is the spin energy. And we've already seen that's a constant of the motion. So we can kind of just wish that away. So we will redefine our energy by just moving the zero of it to be E minus that spin energy, since that's a constant. That way we won't have to worry about it. Now if we look at what we got left here, this is a kinetic energy term in theta dot, so that's our nutation happening. This is potential energy. Now this term here is actually a kinetic energy, but we've seen this before. If you have a kinetic energy that you can write purely as a function of position, you can define that to be an effective potential. You can roll that in with the potential energy into an effective potential. Whoops. So our effective potential will be V of theta is equal to LZ minus LZ prime cos theta over 2I sine squared theta plus MGL cos theta. So this is really a kinetic energy term, but only depends on theta, so it's a function of the position. So it acts like a potential. This actually is a potential energy term. But this means that we can focus on just the theta coordinate alone. So we're down to our E prime equaling 1/2 I theta dot squared, that's a kinetic energy term, plus our effective potential. All right, well, we know how to analyze that, at least to find the churning points of our nutation, theta 1 and theta 2. We can do that by plotting our effective potential as a function of theta. It's going to look something like that. And then we just go and pick out our E prime. And we circle where they intersect. And there's our turning points, theta 1 and theta 2. Now, depending on whether you have fast or slow procession, there's a couple different modes of nutation that you can have. There's actually 3 of them, although one's an edge case. So there's my theta 1, theta 2. One possibility I have is just it kind of bobs back and forth like that, and the motion both at the top and the bottom of the nutation is in the same direction. We can also have it, depending on the initial conditions, kind of go and do loop-de-loops. So going this way down here, but it'll actually go retrograde up on the top. And then the edge case would correspond to scallops, where you come to a momentary halt on the top and you're just moving at the bottom. So we can pull this out by saying, well, LZ is equal to I phi dot sine squared theta plus IS S cos theta. And for depending on the value of theta that you have, it could potentially force some phi dot to go negative. So to get our mode C, if we call this A, B, and C, to get our mode C, that could only occur if LZ over LZ prime is equal to the cosine of theta 1, and then that at that point theta dot equals phi dot equals 0 at theta equals theta 1. So that's the condition to kind of get that scalloped nutation. All right. In the final video of this series, we will be taking a look at a couple of applications. We will be exploring the gyro compass, and we'll be taking a look at the rotational stability of a wheel, or why it is that when you're a kid, you finally discovered that the only way to keep the bike from falling down was to pedal as fast as you possibly could.